Scott Steketee, a former teacher, software developer, and professional development and curriculum writer, is going to present to you some of the things that you can do around pi and circles for Pi Day using Sketchpad. And without further ado, Scott, take it away. Thanks for joining us, everyone.
Okay, welcome. I'm excited to be doing this this first of our new series of webinars, and I've prepared quite a number of different activities that we'll take a look at. I will pause at several points for a chance for Andres and Elizabeth to acquaint me as to what requests, questions, ideas, and suggestions you may have registered via the chat panel. So please go ahead and do that.
Scott, you need to take control. You need to take control of the screen.
Got it. Thank you. There we go.
Perfect. Thanks.
Okay. So I will pause it several times, and I'll take some time to answer questions. Which pieces of what I prepared I get through will depend to a great extent on the sorts of questions people have. The entire presentation sketch will be available to everybody through a link that will be provided to you, and I think it's going to be just online with the archived webinars, but we can get clarification on that from Andres and or Elizabeth later. Okay, so the agenda for today, I have four different parts of the webinar planned. The first will be just some simple build them from scratch sketches that are suitable for relatively beginning Sketchpad users. I have a number of slices of pi, various ways of dissecting the circle in order to approximate pi, and sort of a historical note about Archimedes' work in pioneering that several millennia ago. We'll have a section on pieces of pi in which we'll use some piecewise functions involving pi, sinusoidal functions specifically. We'll create piecewise functions that bound the shape of the letter and then fill in the area between the two functions in order to produce the shape of pi. And we'll have a bit of musical pi in which we'll use, again, sinusoidal functions, which, when they're registered as variations in air pressure, produce musical notes. And we'll use sound buttons to produce some various tones. So those are the items on the agenda. So let's take a look at a first simple build from scratch sketch. And in this one, the build from scratch is going to be the measuring tool, but what we have here is 5 circles. This is an opportunity for students to create their own measuring circle, to do their own measurements, and see what they can find out. So we have some directions right up here. Use the compass tool to construct circle AB. So here's the compass tool. Here is circle AB. And we will actually make it circle AB by using the text tool to label the points. And then we can use circle AB to measure its circumference and construct and measure a radius. So here's a radius using the segment tool. And here's the measure of the length of the radius, which we will label R. So we are going to label that distance measurement as R. And we are also going to measure the circumference of that circle and label that distance measurement as C. So now we can measure our circles. So let me do this little tiny blue one in here. Okay, that's getting pretty close. Let's see. Just adjust it a little bit. Yeah, that looks pretty good. And we're going to make a table now of these three measurements. Whoops, three measurements. Oh, calculate the ratio. So the ratio of the circumference to the radius, from the number menu, we'll choose calculate, take the circumference, divided by the radius.
Scott, can I interrupt for just a second?
Yes, indeed.
Could you close your formatting bar if you don't need it? It's kind of distracting.
Yep.
Thank you.
Thank you. Okay. And we can use properties if we want to see this, this ratio in more detail. So from the properties, we choose the value panel, and let's say 100 thousandths. So there's the ratio. Now we have three measurements from which we can make a table: the radius, the circumference, and the ratio. And new tabulate is in the number menu. So we create our table and double click it to register those results. And now we can measure each of these circles in turn and see how their measurements compare to each other. So now I'm measuring the yellow circle, I double click the table, and I get a new set of values, new radius, new circumference, and so forth. So this is a relatively easy student construction in which students can basically measure lots of circles and find, as they measure lots of circles, that the circumference and the radius change for every circle they measure, but remarkably, the ratio never changes. So this is an activity the kids often do with in elementary school with various round shapes and in geometry class, and it raises an open question, by the way, that I've posted down at the bottom. Is it better to use the radius or to make the extra effort to construct a diameter when you're doing this? And that's the question of whether we get as our ratio 6.28, 319, or whether we get 3.14159, whether we get pi or whether we get 2 pi as our ratio. Fi-Hart has some truly interesting YouTube videos on this topic. So a second activity, also suitable for very simple Sketchpad construction from a blank sketch, is again a circle AB, a radius R, and we're going again to make the same measurements and make a table. Oops. So measure the radius, measure the circumference. I'm sorry, I'm fumbling the mouse. My bad. I also noticed that I often keep my my default set to measure in pixels because of the sort of sketch building that I often do. And I don't want to saddle students with pixels, so I will use the edit menu to change the preferences rather than pixels to use centimeters as our measurement unit. And again, we'll make a table from these two values. We'll collect lots of data for different size circles, And in fact, I can animate point B, select the table, and by right-clicking the table, I can tell it to add table data, 10 new values as the circle changes in size. So by clicking OK, I'm now going to have, as my circle animates wildly, I'll collect a whole bunch of data. So now I've got 10 new values of data, and I can plot this table data and see what happens. So from the graph, plot table data, radius as the x value, circumference as the y value, click OK, and we see several things about the resulting graph. In fact, if we plot some of these, if we connect some of these points, we see that they're on very much of a straight line. And in fact, they're on a straight line whose slope is once again 6.28. So there's another way to investigate pi from simple circle constructions and use a graph this time as we get the value of 6.28 from our measurements. Okay, one more sort of from scratch construction that is suitable for very young kids, but is actually a little surprising. One of the things that kids love to do is to animate with Sketchpad. So here I've just put together a little animated face that the kids might make using circles and arcs of circles and so forth. And we can, this is the sort of thing that kids love to do. So getting things moving in circles, and actually the smile is controlled by a point on an arc that moves up and down on a line. So that combination of the two most natural movements that kids want to use in Sketchpad are movement along a line and movement around a circle. So those two motions, if they're combined, can give some very interesting results. And in this little construction, what we're going to do is to take advantage of the observation that Freudenthal made quite a few years ago, that sine is a wonderful example of a mathematical function that can be introduced graphically from the circle rather than algebraically. So we can do that and have a little fun with it at the same time. So what we're going to do here is to make one of these figures go around the circle. So to make her go around the circle, I got to put a point on the circle, and I'm going to attach her to that point, but I want to attach her in a way that gives me a little bit of flexibility where she actually goes. So I'm going to offset the center of the picture from the circle just by a small segment to give me control of what's happening. I gain that control by taking the point on the circle and translating it using this segment as my vector. So after choosing transform, after choosing translate, I click the 2 points representing the foot and head of the vector, and I get a translation by exactly the same amount as the vector. So my translation, my vector down here, controls that translation, and that allows me to take this picture from the edit menu, merge the drawing to the point, and then I can control exactly how that relates to the point, and that relationship will be maintained even when I animate her once at, let's say, medium speed around the circle. So there she goes. She's animating around the circle. I can, if I like, change the vector to change how she relates to the circle. But every time I click this button, she's going to go once around the circle and stay in that same relation to the point that's on the circle. Now I'm going to do the same thing with linear motion with our friend over here. So I'll put a point on the horizontal line. I'll make a little offset vector for him and translate his point by this vector and merge him to that point. So if I actually want him walking along the line, I can change my translation so that he walks along the line nicely. And once again, from the edit menu, I create an animation button that will animate this point along the line at medium speed. So now we have one figure that can go along the line, another figure that can go around the circle, and we'd like to see how those two motions relate to each other. So one way of seeing how they relate to each other would be to say, well, let's keep track of where this guy is as he walks along the line by having him hold a vertical pole. And we can make that vertical pole by selecting the line and the point that moves, constructing a perpendicular. It doesn't look like he's holding it, does it? Let's see. There, that's a little bit better. Now he's holding the pole. And let's see if that works right. Yep, okay, so he's prepared to walk along holding the pole. And let's do something similar with the figure that's animating around the circle, giving her a horizontal pole to hold. So here's the point on the circle. Here's the horizontal line. We'll construct a parallel. And once again, it doesn't look like she's holding it, so let's make her hold it. Right there, looks good. Okay. So now she can move around the circle while she's holding her pole. And what we'd like to see is the relationship between these two motions as she moves around the circle and he moves along the line. And one way of looking at that relationship is by paying attention to this point right here. And once again, I'm going to make a little translation vector and translate this point by this new vector in order to attach a pencil to it. And I can adjust my pencil so that the point is right where I want it to be. Now I have some extra points here that I don't care about so much, so I'm going to hide those, the points that actually identify the objects themselves that are moving. I'll hide those to clean things up just a bit. And to make this pencil actually work, I'll select the point at the tip of the pencil, and from the display menu, we'll trace that intersection. And let's make it a nice thick pencil by making that dot large so it'll make a nice big trace. And I'm ready to see what happens as each of these figures moves. So let's get this guy back to a starting place, animate him and see what happens. Okay, he makes a a nice straight line. What does our figure on the circle do? Well, moving that pole up and down produces a vertical motion. So we're using the circle to produce vertical motion. We're using the line to produce horizontal motion. And we'll do one more thing. We'll make a way to reset both these points to an initial location. So the horizontal moving figure will start at the center of the circle. The circular moving figure will start right here at the right edge of the circle. We'll make that happen with a movement button that takes this point to the center and this point to here. And I'm going to call that reset. And we'll make it move instantly. So that's what reset does. Now we also want the two of them to move together at the same time. So I'm going to select both of their animation buttons and turn those into a presentation button. They should both move simultaneously. That's fine. And they should stop after the first one of them stops. In other words, after she goes around the circle once, that'll be enough time to stop. So click OK. We've got a reset button and a present button. So we're ready to go. Let's present it. Here they go. So that's kind of a nice result for that is readily accessible to even elementary school kids who just experiment a little bit with animation, a little bit with making figures of their own, and it actually produces a very lovely curve that they won't meet formally until much later. The high school variant of this activity I'll show very quickly in a new page. The high school variant of this approach is to start with a circle. Define that circle using the graph menu as our unit circle. Put a point on that unit circle. Measure the angle from the point 1, 0 to the origin to the point that's moving around, or even better yet, measure this as a construct an arc and measure the arc, because that gives us something to see as it goes. So if I make that arc nice and thick, whoops, that's the circle I've selected. Now I've got the arc. Use the display menu to get this right. Make that nice and thick. And now we can see how the arc will go all the way around. We can measure that. Take the arc, measure the arc angle. And I would like to do this in radians, so I'll use, again, preferences to change my angle units to radians. And I'd like to see that value with at least 2 decimal places. Okay, and we can also measure the y value, the ordinate of point B, and we can see how that ordinate changes as the arc angle changes. And when I do this with kids, I actually make sure that I have them tell me what's the largest value you ever see for y, what's the smallest value you ever see. I want them to be thinking about the behavior behavior of these two variables with relationship to each other before we actually plot the value. Now we can plot the angle measurement and the y value. The y value is a function of the angle measurement. Whoops, got the wrong command there, not on axis, plot is xy. There we are. We're going to trace that point. And animate point B around the circle. And of course, we get a very similar result to the result that we had with the two little stick figures. But here we have additional possibilities that we didn't have before, possibilities that are extremely valuable. For instance, we can at the same time say, well, what happens if we look at the x value of point B instead of the y value, so we can develop the cosine? And what if we look at the ratio and we can develop the tangent, and we can have all three of those animating at once? We can also, instead of just tracing this point, we can actually construct this as a locus. So by selecting point B, which drives the plotted point and the plotted point itself, and so you see this clearly. I'm going to erase the traces for the moment and actually construct that locus. So we have an actual construction now and not just a trace of where the point happened to be. Okay, so that's the set of constructions from scratch that I had prepared. Let me stop and see if Andres and/or Elizabeth can summarize some questions, some thoughts, some suggestions.
No, there was, there's been, I think people are at different levels. I know for people that are new to Sketchpad, you're showing them quite a bit all at once, so it might be a little overwhelming. For those people that have some experience with Sketchpad, this is probably pretty awesome to see all the stuff you can do fairly quickly. One interesting question that came up, if you could go back to the previous page, Scott?
Yep.
So the question there was, the question was, did the two of them move at the same speed because you set them to move at the same speed? And I think you did, right? You made them both go medium.
Yes, that's important for this activity. In fact, if I had changed these, if we look at animation properties, we see that the animate properties have them both at medium. If this figure goes around the circle considerably faster, which we could do by changing her speed to fast, then we'll see what happens if the two motions are not at the same speed. And here we go. So we see a much shorter curve than we had when they were both at the same speed. Or if she goes more slowly, we're going to see the curve very stretched out. We don't even have enough room for that on the screen.
Okay, so that's fine.
So comparing those two is interesting, and it's also interesting when this might even be more interesting to make her go slowly and not make her go once only. So now the presentation, whoops, I meant to make her go fast. Sorry. Fast, there we go. So now the presentation, we can actually see how there are two cycles in the same space where there was only one cycle before when they were moving at the same speed.
All right, great. I mean, we actually, Elizabeth replied with, that'd be a really fun thing to experiment with, which you've just shown us right now. But I think we're good. I asked people to kind of give us a sense of their background in the chat panel, and it looks like
Oh, good.
we have a predominantly sort of intermediate group with some beginners as well. And I mentioned in the chat panel, but those of you who are beginners, and if you want a more gentle introduction to the Sketchpad, I have a webinar I'm doing in April. I believe it's April 23rd, which will be specifically geared towards people that are brand new to Sketchpad. So you are welcome to join us then, and also the video and the materials from today's webinar will be posted. I sent out the links earlier, and I'll send them out again at the end of the webinar so that you can refer back to the video later if you'd like. All right, thanks, Scott. I think we're good.
Now, I did want to start with some things that involve construction from scratch. The next set of activities are prepared, and in a sense that makes them suitable for a wider audience because they're probably useful for folks who are pretty familiar with Sketchpad, but they're also relatively easy to manipulate for folks who are new to Sketchpad. So this is actually sort of a historical investigation of Archimedes' approach to figuring out the value of pi. And he came very, very close for somebody who had at his disposal only the mathematics and the computational capabilities of his era. So what Archimedes did was he started with a circle, and he began, as much of Greek mathematics begins, with an equilateral triangle inscribed in that circle. Not inscribed in the circle, but from the center to the radius, and rotated that successively around in order to create a hexagon within the circle. And of course, they knew that it was easy to do that by taking the same compass that made the circle itself. That same compass strikes off the distance from the first vertex to the two vertices adjacent to it, and so forth. So that was an easy thing for the Greeks to do. But Archimedes took this one step further because he said, well, this hexagon obviously has a shorter perimeter than the circumference of the circle. But what if we also created an outer triangle and used it to circumscribe the circle? So the circle is circumscribed within the outer polygon, and within that is circumscribed another polygon. So the outer polygon is obviously longer in its perimeter than the circle's circumference. The inner one is shorter. So the length of the circumference has to be somewhere between those. So it was, it's easy enough with the mathematics that the Greeks had available to them to measure the perimeters or calculate the perimeters based on the radius, and they did so. That's what Archimedes did. And he found the ratio of the average of the two perimeters. So here are the two perimeters in our example right here. So the average of those two is 62.1, and the ratio of that to the diameter of the circle was 3.23. And he didn't express it in those terms because they always used rational fractions. They didn't have decimals. But that was the result that he got for the hexagon. And what Archimedes then did was he said, well, if I can do that for the hexagon, if I split that triangle in two and use this point as a new vertex, then I'll have a 12-gon. So I'll put a 12-gon inside my circle using half of that triangle. And I'm going to hide the circle right now so that you can better see the 12-gon. So here's the inner 12-gon and here's the outer 12-gon. The circle is being squeezed between these. And now the average perimeter, the average of the perimeters of these two 12 guns divided by the diameter of the circle is now 3.16. And this is getting very close very quickly to a number that, that looks quite familiar to us. Well, Archimedes did some extremely laborious computation for his day and doubled it again by using still a smaller triangle, and again, to the point where we can't even see on the screen the difference between these two polygons. And that's how Archimedes got his extraordinarily accurate value for pi. So this struck me as a wonderful demonstration of what the Greeks were able to do with the limited calculation capabilities and the limited mathematics that was available to them at that time. But it's also quite striking to me in the sense that there's much about Archimedes' approach here that presages some of what Newton and Leibniz began to do in calculus. And so what we do in integral calculus, trying to find the area enclosed by a curve, and we do it by going to smaller and smaller pieces and squeezing the function itself between something that's greater and something that's less in order to be sure that we're really approaching the appropriate limit as we go to smaller and smaller pieces. So that anticipation of calculus that's inherent in what Archimedes was doing seems very interesting to me. And it also seems to me something that geometry students can understand pretty easily from a demonstration like this, and that will give them a leg up when they get to thinking about calculus and area bounded by various kinds of curves. So that's Archimedes' calculation of pi. If there are any questions, break in, Andres or Elizabeth. Otherwise, I'll go on to a similar, very old approach to area of a circle.
I don't see any questions right now, Scott. Thanks.
Okay. I've got a couple of demonstrations. Actually, I'm gonna reverse the order of these, because although this is very similar to Archimedes' approach, I think it's a little different, and I don't know for sure that one is attributed to Archimedes. This one I've definitely seen attributed to Archimedes. So the next question, I mean, pi arises as the ratio between the diameter of the circle and the circumference. But the Greeks were very, very eager to find areas as well. And this particular thought experiment of Archimedes it seems to me to be an extraordinary way to think about it. Imagine the circle as being composed of a coiled rope. And I've got concentric circles here because they're a lot easier to draw than coils. And in fact, from a mathematical point of view, that actually makes the problem a bit simpler because it's a bit cleaner. So take these concentric circles, which form the interior, and we're going to keep them sort of separated. They represent the interior. I haven't tried to fill the interior with them. I could. I have control of the number of strands of rope. So if I just make more strands of rope, I can completely fill the interior. But let's leave a little space between them so we can see what's happening. Let's cut the rope. And once we cut these ropes, let's unroll them. And we find that the longest rope, the one that formed the circumference of the circle, is 2 pi r. We knew that from what we already learned in the last sketch about the relationship between the circumference and the radius. And they've arranged themselves so nicely into a right triangle with a height of r. So now from the height and the base of this right triangle, we're in a very nice position to figure out how the area of the circle relates to pi and to the radius. And that just seems like an extraordinary way to me of turning a circular figure into a figure that has no circles at all. I have a second dissection that is very similar to this, and I'll go on to that. So this is again Archimedes hexagon that we saw from the original investigation.
Hey, Scott, can I stop you for a second?
Yep.
Stop. Yeah. The people are finding this really cool. Some questions came up both 2 models ago and the last model. And before we go into another one, I thought maybe we could stop for a second. If you go back to, while you're here, the question was, how do you do the cutting and the unrolling of the triangle? I'm assuming it's much more, is it pretty complex, or is it?
It was a little complicated to figure out how to do it, indeed. You would need to sort of reverse engineer the sketch that I did. These individual strands in here are an iterated image. So the one that's really critical, and the one on which all the others are based, is this outer one, which is its own segment. And it's a segment now. You notice in the status line down here at the bottom right of the screen that what's selected is an arc. So this is actually an arc. And what I had to do, if we look at the properties of this arc, we see that it's centered at point number 5. Well, wait a minute. How can that be centered anywhere? Because it's straight here. So what I actually had to do, let's put it in a partially unrolled situation. What I actually had to do was to figure out, keeping the length of the arc the same, where would the center of the circle need to be in order for this arc to be in the correct orientation to be unrolling. So if we look at it here, and again, look at the properties, centered at point number 5, so there's the center point, and I did a calculation which allowed me to figure out how much of a dilation to do, and I actually have, well, BA and BC are actually these objects right here. So let's leave this visible, and we can drag point C here and see how this changes. When we're at the circle position, this ratio becomes 1, so the center is just the center of the circle. As it moves out, it's moving out faster and faster. So it's still an arc, still starting at this point, but the center of the circle is going farther and farther away, and it goes not quite to infinity, because I hedged this a little bit. If it went to infinity, the segment wouldn't exist anymore. But it goes out 250 times, and you can't really see very well that this last segment is not by now straight. I would have to send this ratio to infinity to make it straight, But 250 times as far as the length of the radius is quite adequate to make it straight as far as we can tell looking at it on the screen.
Wow, that was cool. I'm surprised you're able to actually break that down for us just on the fly right there too, Scott. I had one other question just about the previous
I
model.
wish it had been that easy to create when I
I
first
know.
built the sketch. It took me,
Well, people
you
people
know,
are
it took
excited.
me a number of false tries before I figured out how to build the thing.
Yeah, people are excited that they'll get access to this sketch that they can use it as a presentation. On the previous model, the one, yeah, how did you? It's oh yeah, this one. How did so? The question was, well, first of all, what the question was, why did you double each time? But I kind of get. I'm assuming that was sort of Archimedes' approach, starting with the equilateral triangle, which you knew, and then just splitting it in half again. But then what keystrokes were you using to double the parameter each time?
I wasn't using keystrokes. I was using a button.
Okay.
So I have a double parameter button here in the sketch, and what this button does is to move parameter n toward a calculated value, which I left hidden, of 2 times n. So I have n and a calculated value of 2n, and a movement button is just going to move n to 2n.
Okay, great.
So that was the doubling method. If you use such a technique, by the way, I've made this mistake multiple times, be careful when you create your button that it's either an instant movement button, or if it's not an instant movement button, that it moves towards the initial destination. Because 2n is going to be a moving target. If n gets to 7, 2n is now going to be 14. So n is never going to get to 2n. And if it tries to follow the moving destination, then there's going to be big trouble. Ready? It's never going to get there, and it's just going to keep going and going and going and going forever. So doubling won't work as a result of that change. So I have to remember not to save this sketch now when I'm done with the presentation. Okay.
Great, thanks. Let's go on to that other model. I was getting, yeah, this one's cool. Thanks.
Yeah.
Thanks, Scott.
So this one actually, sinking your teeth into it, this is the one with the teeth. So this is a similar dissection, but with a little bit of a variant to it. So we're going to do some unrolling here too, but we've split the circle along all these sections, and the only pieces that hold together are the two semicircles that border the green and the blue. So we'll unroll the green and the blue. So there are the teeth, and if we slide the teeth so that they interlock, we get something that looks very much like, although not quite, a rectangle. And let's see if I can move the whole thing over so you can see the whole thing. Yeah. So that's with n equals 5, which, since I divided in my construction, I divided it into 4 pieces. So each of these 5 is, this gives us 20 sectors here. And we can change the parameter right now if we want. Just select it and press the plus sign a few times. And we can see by pressing the plus sign, each time it gets closer and closer to straight lines instead of little arcs, because the arcs are getting so small that there's very little curvature left to them. So this again is a nice way of showing how the circle can be changed so that you have essentially a rectangle. If we went to, for instance, 100, it would be very difficult to tell the difference between that. The scalloping on these arcs is almost totally straight here. So we have here's the blue part of the circumference, half the circumference, here's the green part of the circumference, and the height is the radius. So that's also a nice way of dissecting the circle into a rectangle this time instead of a triangle. I've got one more that uses triangles, by the way, and this one's with a slider, and the basic idea is we take these 6 triangles, we separate them, and I don't have an animation that separates these. At some point, I may try to take the time to actually show the breaking of the circle apart into these 6 sectors that are sitting down here. But I thought it was enough to actually be able to, by changing this parameter for the depth of the iteration, to change the number of sectors into which we divide it. And then one of the things that we know is that if you take a triangle and shear one vertex by moving it parallel to the opposite side, that shearing maintains the area. So here, all the triangles are being sheared, their areas are not changing, and they actually form one triangle whose base is the circumference and whose height is the radius. So that also seems like to me like a very nice dissection, and I'm pretty sure that this is original with Archimedes as well. So there are several prepared sketches that are all set and ready to go for you. I got to show you this one real quick. I just went crazy with this one. It's a similar one to the last 2 that we saw, but I can take the sectors of this circle and arrange them, and each one is trying to follow the one next to it. So this one is trying to rotate around to line up next to the one next to it, and its neighbors are chasing it, and its neighbors are chasing their neighbors, and these guys are all chasing each other, trying to line up next to the sector that they started next to, only flipped in direction. So here they all come, and I just enjoyed the visual imagery of this moving, and eventually forming the rectangle. I got so carried away with this one, I decided that it also made sense to be able to randomize the colors so you get different color arrangements. And then you can reassemble them into a circle. But we're not going to take time to do that. I want to show you quickly the rest of the things that I have prepared for you in this sketch. I'm sorry that we didn't have time to do them all. I did take a series that allows you to calculate pi. Here's this series calculates the arctangent. The arctangent of 1, the angle whose tangent is 1 is pi over 4. So you can calculate pi that way pretty easily. I've put the 4 into this calculation here, and just to show very quickly what you do with this, select the 4 parameters on the left, hold the shift key down to iterate to depth, where the depth is going to be 5. D1, this is the denominator. The denominator has to go from, imagine this as 1z over 1. Denominator has to go from 1 to 3 to 5 to 7, so we add 2 for the denominator. The sign has to go from +1 to -1 and back again, because it's positive, negative, positive, negative. So that's what this does. So that goes to here. And the sum goes to the sum plus 4. There's where I put the 4 in. I stuck the 4 in so that we'll actually get pi out of this, times the sine over d1. And I don't need to worry about the z cubed because z is 1. So z cubed, z fifth, z seventh, they're all going to be 1. So that goes to this. And There we have a table that iterates it all. And if we go up to 100, depth of 100, we see that we're getting to 3.15, 1514 instead of 1415. Well, this doesn't converge very quickly. Okay, there are a bunch of other sketches here that I think you'll enjoy. I'm sorry I didn't have time to do the piecewise function, but this sketch, the presentation sketch, has a whole set of pages here explaining in detail how to use the piecewise function tools. And the basic idea of it is we have two sine curves, and we've created a piecewise function here in which this bottom sine curve drops to the axis and and switches. This is a different piece of the function, and then it switches back to the original sinusoid, and then it has another piece that's down here, and then back to the original sinusoid. And in that way, one function forms the top of the pie, the other function forms the bottom and the two legs by inserting these two pieces that are on the axis instead of the parts that would be here in the sinusoid. So I've got those for you to take a look at. I've got some examples of musical functions. This is the amplitude. We're taking the sine of the frequency times 2 pi x. That will give us 440 beats per second. And so this particular function with 440 times 2 pi x, 440 complete cycles per second, we can actually listen to it. Can people hear that? And we can go up an octave, down an octave, up a third, and so forth. And I've got some musical sketches that relate to this, including, for instance, a piano that uses these functions so we can play. And finally, these are the Sketchpad resources that are available to you. We have online tutorials that are free. We have a bunch of free activities, activity modules. Sketch Exchange is a wonderful resource. This is about all the training activities that are available. And what this is actually an image from the web page at keycurriculum.com/products/sketchpad, Sketchpad resources. Okay, I'm sorry to run so late into our time. Oh, and I should mention, in terms of training, the online courses are starting April 1st, and those are some very nice online courses for all different areas of mathematics and all different levels of Sketchpad expertise.
All right, Scott, that was phenomenal. Very impressive, very inspirational. There's a lot of sketches there, and certainly it seems like you have plenty of material for more than just one webinar. So hopefully we can.
Yes, I did. I overdid it.
No, it's okay. In part it's because we've had a little bit of a couple of months of not doing webinars, so we've got all those pent-up ideas and things we want to share. But we definitely need to set you up to spend more time on some of the other things that the rest of you will find in the sketch. I posted it in the chat panel just a moment ago, but I was talking to Darren, our webmaster, and he said that Scott, you just need to give us the sketch right away, send it to Darren and me, and he can get it up tonight. And that way, those of you that are out there that would like to use this tomorrow for Pi Day, it'll be available at both the McGraw-Hill education site link I sent you earlier, as well as the Key Curriculum one. So yeah, Scott, that's just a matter of you getting the sketch to Darren.
Okay, I'll do that right away.
And I don't, let's see if I can get the link back in there. I'm having troubles. And then also, I'd just like to remind everyone about the, at the very beginning, I sent out a link for the Pi Day, the McGraw-Hill Pi Day page. So that I can put back in here. Let me just do this. All right, so the free apps and resources at McGraw-Hill Online for Pi Day are here. In just a minute, I'll try to put the links back in for the 2 places where you'll be able to log in to get today's sketch. And just want to say, Scott, fascinating as always. Thank you so much. Thanks for everyone for joining us this evening, and we will here the 2 links where you'll be able to download the sketch, and we'll post the video of this webinar soon. And it's just after 5, so thank you for joining us, all of you that are out there. If you have any more questions, you can use the chat panel. We'll be on for a couple more minutes, but this is officially the end of the webinar, and thanks again, Scott. And thanks to all of you.
Thanks to everyone for coming.